For example, I know that some of you, I think, work on the flow above a rotating disk, and it too shows this. If you measure things in the right units, you find that this is turbulent laminar, turbulent laminar, turbulent laminar, and that spacing is about the same spacing as in the right units as in the wet case. Okay, here's a film of the computation of the formation of these turbulent laminar bands. At Reynolds number 5, okay, what you're seeing here is the streamwise velocity. So it's, you can sort of see it, it's going to the left, the red stuff is going to the left, the blue is going to the right, and these are the streaks. Remember we talked about streaks, what that means, this is the span-wise direction, this is the streamwise direction, and we said that, here, let's start it over. Start from here. Let's stop it. No, that's not what I need to do. Let's just look at this frozen. These are streaks, red, irregular streaks in turbulence, but they're still present in turbulence. Red, blue, and this distance tells you about what is the distance in gaps, because this really is the little roll structure like this. So the distance between the top and the bottom plate, which is over here, is about like that, or rather two of them. It's about like that, whole wavelength. Okay? No, actually not. It's about like this. This is the distance between the two plates. One of these red, one of these blue. And these things have no problem. They're directed exactly in the streamwise direction, as you would expect. You know, what you're doing to this plate is moving it like this. So it's not surprising that you see structures that are lined up with this direction. And why there's variation in the span-wise direction? Well, you just heard kind of an explanation vaguely. It's not clear why, but okay, let's just say people have studied it. So this is what turbulence looks like at Reynolds in plane chord flow at Reynolds number 500, which is not very high. And it's turbulent. You can see it's moving around irregularly. It's not. It's called fully developed turbulence. Probably most of you have heard of the Kolmogorov spectrum. That's not that's what you get at high Reynolds number. This is not high Reynolds number. This is all transitional. Now we play the movie again. Yes?
I mean, in this video, the contours represent the
streamwise velocity. There, with red and blue being negative and positive. And it's in the mid-plane, so that if it were laminar, everything would be green.
Okay.
There would be, because the streamwise velocity is 0 at the mid-plane, because you have equal and opposite. Okay. What you're seeing is rolls like this that are pushing up the red and pushing down the blue. And now we decrease the Reynolds number to 350. And you see these streaks, the red and blue, you see them organize themselves spontaneously. And you see this is all green, which as I said would be the case if it were laminar. That is to say, no motion, no streamwise velocity. And you see the beginning of this band, but if you give it enough time, and it's going to actually be quite regular. It's taking its time here, but you certainly see it wants to do something like that. It's a 24-degree thing. And this distance, you can see, is much greater than the distance between the plates, which is there.
Sorry, Professor. So people still not really clear why they make that angle.
Yes, that's right. I think maybe some of us know why it's not 0. I'm not even sure of that. Okay. And it'll just persist indefinitely. Yes?
I'm a bit confused because you said that little thing in the middle was the size of the plates, but then how are you getting a wet flow? I'm confused as to this physical system behind that video.
Okay, I'm sorry. Hold on. Why shouldn't I make a numerical simulation of...
this is
it's simulation.
Yes. Yes. Okay. But even if, but I don't even understand why the question would be asked if it were, supposing it were a very, very good experiment with lots of color measurements, why shouldn't I be able to do that also? What is difficult about this?
Well, you just said that this is the size of the plates, like the spacing of the plates.
That's right.
No,
But the plates are here.
Oh, yeah.
That's what I thought maybe you didn't understand. The plates are here.
Never mind.
Okay, this is a view of the midplane. This is cut between the plates. So I'm not doing anything weird. This could be experiment. If you could do an experiment that well. Yes.
Is this streamwise velocity or velocity?
Streamwise velocity, but that's the same because for the laminar flow, it's, and for the average flow, it's 0 in the midplane. Remember we're doing this? Right. So it's one of those lucky times when you don't have to think about which one it is. Okay. Okay, so that's nice, and let's do a little bit of quantitative study of these bands. As pretty as movies are, and as nice as it is, isn't it amazing how much more fun it is to watch movies than to watch lectures? I mean, you could watch movies all the time. It's no wonder that this Khan Academy is so successful. If it's, as long as if it's a real person in front of you, not so interesting. If it's a movie, oh, no matter what the movie's doing, it's interesting, no? But especially movies of physical things. Okay, so what am I doing? This is a numerical simulation. This set of simulations was done with code called PRISM, very similar to your Semtech. Later I switched to the one that Gibson uses, the one who did all those steady states that I showed you. And what am I going to show you? Again, the mid-plane, this is the middle between the two, and I'm going to show a bunch of points that vary in what I've called, okay, this uses a trick, which I'm not, well, this Z is not, am I going to explain all this? I guess I am. I think I'm going to have to. Hold on. Yeah, I guess I'm showing this. Yeah, I think I have to go back to my first picture. Okay, there's a trick in these simulations. Okay, I explained this before about Faraday and other things. This simulation was not done in this big box. The other one was done in the big box. The movie was done in the big box. But this one was not done in a big box. This was done in a bunch of small boxes. And can you see, oh, you probably can. You can see these white, can you see a white line here? Can you see a rectangle? A little bit? Can you see a grid of rectangles? Let's turn off the light. The light here?
No, it's over there.
It's over there.
Yeah, press the screen.
Oh, yeah.
There you go, shows you.
Ah, yes, it does. Wow. Okay.
I think the top left one is probably everything off, isn't it? That one.
Ah, that's,
No. Keep
no,
going.
that's what I want.
That's
though.
enough.
I think that's enough. Okay, but I think it's still not that clear, is it? Oh, yeah, a little bit. Can you see white lines here when you really try? Just barely. Yes.
Oh,
Okay.
yeah, okay, now.
Wait, okay, so these simulations were actually done in rectangles like this. So these rectangles are tilted, knowing what they saw experimentally, the angle. So it's tilted down. Note that this is an enormous savings. If you did this, you would have to capture this whole
Wider.
thing. But here you can do this in a narrow rectangle like this. And this is how we did it. We did it with periodic boundary conditions here and here and here and here. And the direction that I'm calling Z, because sometimes I call it Z prime, is this one. It's the direction in which you go from turbulent to laminar to turbulent to laminar. It's not the spanwise direction, for what I'm going to show you here.
So you tilted 24 degree already
Just
from
so.
the beginning.
That's right. It's tilted 24 degrees from the beginning.
That's
Okay,
smart.
but we've done them in big domains too. It's a robust phenomenon, but you can calculate more economically.
That's smart.
You can only, if you do such a study, you're not going to find out what's the angle that it likes, because you've given it the angle, but you will compute the pattern that exists at 24 degrees. Anyway, so the direction I'm calling Z is this one. Okay?
Are you saying
Yes.
that in other domains, in bigger domains, like you found the same angle or some different angle? Like
Several things happened. One, we varied the angle and found that, I'll be talking about different angles later. Okay, I'll just say that. The movie, as I said, the movie was done in the usual domain. So that you can say that you found it then. And that 24 degrees then could be measured in that movie. Yeah, it's not exactly 24 degrees. It's not attached to its being that.
obviously,
but yes.
around that.
But yes, this can be found also in. Let me see if I turn this up. Does it become brighter? Here? No, I don't. No. Okay, so here I am, and now I've shown you that this is the Z direction, and here's 500, which is where that movie started, and in lowering and there's 32 time traces, in lowering the Reynolds number, you indeed find spontaneous formation of turbulent laminar, turbulent laminar, turbulent laminar. with a spacing of 40. This is a length of 120, so it couldn't have been any old length. I mean, it couldn't have been 50, but it did choose 40 as opposed to 60 or as opposed to 20. And that is indeed, you know, what's 40 half gaps. Okay? And from this, you see it's pretty irregular, and you also see that the laminar region is not entirely laminar. You see there's a lot of stuff going on in there. It is, if it were really laminar, it would just be a straight line. The velocity would be constant. And from this, we can look at a bunch of things quantitatively. We can, okay, this is, again, lowering the Reynolds number. And here you see a bunch of things. You see that as you decrease the Reynolds number, you get fewer bands. This is, here you had 3, and starting here you have 2. You really only have 2 because this is periodic, so this is part of that one. When this one finished, it's not that this one restarted, he belongs here. So this one just finished, so it lowers the number. It wants to have fewer bands, or longer wavelength, as you decrease the Reynolds number. I'm not telling you why, I'm just telling you it's a fact. Eventually it just has 1 by 300, and by 290 it doesn't have any. Okay? So some of the questions you could ask, and some of which I will answer, is what's the upper threshold, what's its definition, and what's its value in Reynolds number? What's the lower threshold, what's its definition, what's its value? What processes choose the wavelength? I think I can give an answer to this top and bottom questions. And how is a turbulent laminar pattern maintained? And I can give, again, some ingredients about this question, some ingredients about this question, and pretty much definitive answers to the top and bottom question. So to answer the top one, about the top threshold, let's take 3 of these time series at different Reynolds numbers, 500, 410, 350. And I'm showing here a track of what? Well, I'm going to look at the span-wise velocity at a particular x, in the midplane, particular x point. Those are the dots I was showing you before. You know, these are the same things I was showing you before in time. If I take the Fourier transform, you can see clearly structure, not structure. That looks like a wave number 1, right? It looks like a sine wave, vaguely. But in fact, that it really is true. If you take the Fourier transform and you take the 1 component, you will see it here appear. If you do that to this, the level is very low. That's what this arrow is doing. This is showing this is pretty close to 0. It's not 0, 0, but it's close, it's small. Whereas here, you can see, okay, here especially, you see that it's quite high. It changes a lot. It's very noisy. You can see it's not a perfect, it's not black, white, and it moves and it's noisy. But you see here that and it corresponds to the peaks. Here you have a lot of, here you have 1, 0, and you see this is pretty high. Over here, it looks kind of uniform, right? And this is lower than that. No, vaguely. Over here too, there's not much of a pattern, and it's pretty low. So you can see this quantitatively reflects what you see by eye. This first component of the first Fourier component, you take the inner product of these with a sine wave, more or less, right? We take the absolute value because we don't care about the phase. We better not care about the phase because see how this one's moving, right? And this one too, okay? And that's what we plot. But it too has very variable values. Doesn't have a single value. So what we do is we plot the probability. We act as though this is these time series are from a probabilistic distribution, and we take all of these values to high and low, high and low, high and low, and we make a probability distribution function of them. How often does a high value occur? How often does a low value occur? What's the probability? And I'll get you in just a moment. And this is what you find for those 3 colors. When it's uniform, sometimes you have some high values of the W1, but rarely. This is the probability. Mostly what you have is 0 as the most likely value of that Fourier component is 0. The green one, the intermediate one, well, it's, kind of, whereas for the banded one, the most likely value is 1. This is a normalized value. So you find a definite peak, and this is how we define the upper threshold. It's not an abrupt threshold. You have this. You don't. We define it by the maximum of the probability distribution. So it's a statistical measure, and this is always the case in these turbulent threshold questions. The definition of the threshold is the main question, not the actual determination of it, but how you're going to, what quantity are you going to measure. You wanted to ask something.
I mean, why do you consider like the span-wise velocity, maybe the span-wise?
Because I found that it was best. I looked at them all. It had the cleanest signal. Okay? And here, I'm mapping as a function of Reynolds number, this maximum, this most likely value of the probability distribution function. And it is, recall that the most likely value is 0 for Reynolds number of 500, yes. And it is 1 for Reynolds number of 350. And here we are, here. And here is where you can see what looks like an actual threshold here, which we measured to be about 430 is what we believe it to be.
And solid and open dots are.
I'm sorry?
Solid and open dots are what?
Two different methods of fitting, yes. In one case, but thank you. In one case, I tried to fit these. I wanted this to be some classic stat-mech thing where I wanted to fit this to a quartic. So I wanted this to go from this to, the picture that I've given you many times, where I'm going to take my finger and push this down and a maximum appears. But that didn't work out very well. I didn't get very good fits to quartics. Nothing worked out all that well, and so it's all like that. Anyway, hence our, is that 20, 40, 68? Yes. So we believe the threshold is 430, 440, something like that. Okay. Which is not what you see, by which I mean, if you look by eye at 440, you think it's uniform. As people were saying the threshold was more like, I don't know, 380, because that's the first time you see it by eye. But seeing by eye is not a very good criterion. It has to be a certain amplitude for it. It's much better to have something which is 0 until it's not, so that you can, a small, this you might think was noise if you weren't following it up by a whole curve. Like this, and seeing that this was a proper trend that you could measure. Yes, someone was going to ask something? Yes.
Why some red dots are below 0?
Yes, that must be the thing that I was doing there, where I was trying to fit this with a coefficient, with a function that did this, and I expected, and I ended up with a sign that was, I expected I would have a positive sign here for my quadratic coefficient, but it didn't. It's something like that. I don't know. I don't remember. But I tried different ways of processing this data, none of which were completely satisfactory, as I said. Okay. This is just to show more cute things that it does. You can see this is just a different run, the same kind of thing. Here, you remember it lost a band over here. Right, I told you that it didn't reform here. This is one of this. So it definitely wanted to have 2. But look over here, it made a mistake. It lost 2 at the same time. It knew it wasn't happy having 3, but they didn't get together and decide, oh, you're the one who's going to go. They both said, oh, there was too many of us, and 2 of them went at the same time, pretty much. But you see, the system wasn't happy having 1. It kept trying to make another one, and another, and finally succeeded, and then made 2. By which I mean, it really wants to have that wavelength. When it has these Reynolds numbers, it wants to have this wavelength of 40. It is not happy having a 1. It keeps trying. And again, at the time I was working on this, I would like some way of processing this data. When I say these words, wants to have 2. They lost 2 by mistake. Those are words you would like to put some theory to, quantify, but I don't have anything besides these words to say about this. I would try to measure this period here. I did, but so what? So it makes these little spurs at this period. I wasn't able to put that together to a theory. Why did this one work out? Why was it moving when it only had 1? I don't, those are all questions that possibly could be answered if you knew the right way to analyze this data. But just to say, it does interesting things, this thing. Here's another thing. This is at Reynolds number 350, at which so many of our measurements were taken. This is 300, quite low. And here, this is where the domain is increased in time. And again, you can see here it has a wavelength of 40. And when the room expands here, it still wants to have a wavelength of 40. It makes another band. You can see it splits. And this is what the profile looks like at this time. Whereas, in contrast, at 300, you may give it a wider domain, and it has no, okay, there's the band here, but it has no desire to, it's happy, okay, it doesn't mind being like this, but it doesn't mind being like this either. We call this a localized state, and it pretty much wants to be far from its neighbors. It doesn't feel its neighbors. This is a genuinely periodic phenomenon with noise, and this one is local, is like a pulse. And it really goes here, it's white in between, and over here between it's not white, it's yellow. It never goes down to being laminar. So this state and this state we view as different. One of them is a localized state, the other one a periodic pattern. Then we analyze the mean flow, again more quantitative things. I'm wondering if we should stop around now or no, I think I'll be finished with this topic shortly and then we'll stop. Okay, so you've seen these series now many times. Let us take an average in time and in x. Remember what x is. X is not the streamwise direction. X is the direction along the bands. Okay, this, yeah, it's the direction along the bands. So it's at 24 degrees from the streamwise direction. When we do that, we get we can look at various hydrodynamic quantities. This is the deviation from the laminar flow. See, there's a blue and a red, blue and red patches, and all these features are reproducible and true. The fact that there's little separation here between the red and blue and a bigger one there. These fields are all smooth because all those statistics have smoothed out all this turbulence, the dx and the dt average. So this is saying that there's a piece that goes faster along here and slower along here, and this is saying that all this is two-dimensional data sets in the cross-channel along perpendicular to the band plane, and in that space the flow here is like this in that plane. That's what this is showing, and this is showing the turbulent kinetic energy, and this is showing the pressure. And let me remind you what it is that's being measured here by the this just shows how smooth the data can become. These are time averages here, and you see that there's no harm in taking an x average. This is what I was talking about. You know, it's a bad idea to take an average of things that vary a lot, that vary systematically, right? It's ridiculous to get the average value of a population's height because you're including the babies as well as the grown people. That makes no sense as an average. You know that there's this huge systematic variation between the babies and the grown people. And so too, average lifespan, when people compare to we were just talking about this yesterday, weren't we? When people compare to the old days and now, also, people say, oh, imagine now we live to be 80 and back in the old days people lived to be 20. I mean, yes, some people live to be 20, but the average lifespan contains a lot of infant mortality from those old days. So you're averaging amounts that are 1 and 2 and 3 with amounts that are 60 and 70, 80. And that kind of makes no sense as an average. You should average things that are similar. I mean, obviously they're not that similar, you wouldn't have to take the average. But where you do the changes are things that you don't understand what you're going to look at or that you can't really provide for. You're going to take the average of an adult population. And there, of course, there's variation. But mainly, they're all adults. They're mostly the same, and you're trying to even out the noise between the different people.
Conditional average.
Conditional averaging, there. That's the word
That's
I'm
what
saying.
these people understand.
Okay, oh good,
Include
thank you.
conditional.
Understand. Okay, so this tells you that taking the average in x is a reasonable thing to do. You can already see from this that taking the average in time is a reasonable thing to do. And this is telling you that taking the average in x is a reasonable thing to do, that all the x pictures look kind of similar. Right, so by the time you're finished, you get a really nice, smooth picture here for each of the quantities. And these are quite reproducible over runs and everything. And here we can do analysis of this 2D flow. It's not 2D, hold on, let me see if I get this picture. Where did this go? Okay. Where did it go? Oh, well. Oh, well, okay, well, I'm here. I can show you, this is a simulation in a big box. And you see that the bands are forming, but they can't, and they can decide that they have an angle and a wavelength, but you see they can't decide on their pitch. In ours, they decide on a pitch because it's prescribed. Our angle is 24 degrees and not minus 24 degrees. But here there are some that are like this and some that are like this. This is a simulation done in 2010 in a big box. But that's not quite what I was looking for. What I was looking for was, oh well, it's not here. Okay, so one of the results is that this data set here of this is the velocity along the bands, right? So you have your apparatus that's doing this, and then you have the bands, right, that are at an angle, and it turns out that there's velocity along the bands, and that is what you're measuring here. This is the velocity along the bands. Okay. Anyway, it turns out that it can be represented with only basically with only one wave number in Z. So that, remember we looked at W1? So that turns out to really pretty much describe it. You can represent it as a sum of constant in Z. Remember, Z is the direction in which there's variation. Your turbulent, laminar. That's what, and cosine and sine in Z. So this is really a tremendous reduction of the information. You used to have X, Y, Z, T. You've averaged in T. You've averaged in X. You now have a data set in X and Y, but it turns out that you barely need much representation in Z at all. And I remind you, Z is not span-wise, it's the... and doing this, you can make a little tiny model. This is a one-dimensional model. That is to say, these are derivatives with respect to Y, the cross-channel direction. And you can represent the flow within the plates by a stream function psi. You have the flow parallel to the bands. That's U, and that's here, and it's got three components: U0, U cosine, U sine. Same thing with the stream function. It's this. And so you'd think, oh, you've solved it, but no, you haven't. This is 6 equations. This is Navier-Stokes projected to average Navier, projected onto this basis. No, you haven't solved it because this is 6 equations in 9 unknowns. This here is the Reynolds stress term, the usual closure problem, and your unknowns are psi, psi, U, and F, and so you should have 9 equations if you wanted to close it. Usual problem. Still, it's nice to have these equations. They might help you understand things. Let us look at the force balance, and we're going to give it a break soon. This is Navier-Stokes, of course, above, and now let us average. We'll average in time. We're also averaging in X. And so this is what we get, the usual thing. All the linear terms just continue. This term splits into 2. One that comes from the average dot grad average, and the other one that's the average of fluctuation dot grad fluctuation. I think if you do fluid mechanics, you're very familiar with this. Okay, so if you have a statistical equilibrium, which we do, you have equilibrium between these forces. You'll have to take my word for it that the grad P is not playing much of a role. I could have drawn it, but it's not. And indeed, if you add up these curves every place, you will see that they are 0, pretty much. It's not exact equilibrium. Okay. This and this and then, okay. In particular, you'll see that in this so-called laminar region, of course, the Reynolds stress is 0, the fluctuations are 0, it's laminar, that's what laminar means, right? But, so what that leaves is the red to counteract the blue, viscous and nonlinear, right? That's the only one we can hope to understand is the laminar region, because we don't know the Reynolds stress. But laminar plane Couette flow is not like that.